Welcome to the second part of this lesson. Here, we're going to begin by talking about what we call the bell jar experiment. Now, a bell jar is simply a container like that, and inside you have an electric bell. Electric bell, of course, connected to electric wires, and then when electricity passes through here, magnetization of this bell, of the gong, takes place very fast, back and forth, leading to gong being hit and sound comes. Now what happens in the experiment is that first and foremost, air is removed using what we call a vacuum pump. Air is removed from this container, like you can see through this pipe, and goes away. So eventually this part is evacuated. You form a vacuum. Then when the bell is ringing, as the air is being vacuumed out, initially you can hear the ringing, but as time goes by, the tone decreases slowly by slowly, and eventually there's no sound that can be perceived. The reason is, like we did say in our previous lesson, sound can be transmitted through a material medium, like air. When the air is removed using the vacuum pump, it means that there can be no vibration transmitted, there can be no compressions and refractions in the air because it is taken out. And that's why over time, the loudness of this sound will reduce and eventually it will be zero. So what is the purpose of this experiment? It shows that sound can only be transmitted through a material medium. Secondly, as the air pressure inside the bell is reduced, the loudness of the sound heard outside also decreases due to the removal of transmitting a medium. And the bell can still be seen as ringing here. The gong can be seen as hitting at this point. The hammer can be seen hitting the gong, but no sound is perceived because there's no material medium for transmission. Now, like we said, sound is a wave like any other. It has properties that are associated with waves. For example, reflection. When sound is produced and hits an obstacle, then it's reflected back. A special name given to that is echo. Now there's a question here which we can use to try to understand what an echo is. A misguided child shouts Chelsea at a nearby cliff and hears an echo 1.4 seconds later. How far away is the cliff? Now take the speed of sound to be 340 meters per second. Like we did say, speed of sound is about 340, 330 meters away. Now speed is the same as distance divided by time. Distance divided by time. We already know the speed. So distance will be the same as speed multiplied by time. So since the speed is 340 meters per second, and the time taken here is 1.4 seconds. Let me call that 14/10. These ones cancel out. You end up having 476 meters as your answer. But remember, from the context of the question, sound hits a wall and comes back. So sound travels 476 meters, that is from the source, from the child, to the wall, and then back. So to answer the question, what was the distance between this child and the wall, it will be half of that. Half of the 476. So the actual distance will be 238 meters. 238 meters, because this distance is the distance that will be taken by the sound to go and hit an obstacle and be reflected back. That is reflection. Again, sound, like any other wave, undergoes refraction. And this is a very good illustration of refraction. Here, we have a source, person A, then we have another figure B and C. Now the sound produced by person A may be heard more clearly by person B than by person C. And this is a simple reason. The situation where we have here person A and person B is at night. At night, it is cooler just above the earth because there is no sunlight. During the day, it is much warmer. Rays from the sun will reach the earth and are going to be reflected back, so the air above the earth will be warmed up and raised up. But at night, it is cooler. So when this person produces sound, that sound is refracted towards the cooler part of the air. And that means it will be transmitted over a longer distance to person B, who is very far away from person A. But person B can still perceive the sound because it's at night, because the sound is refracted over the cooler air. During the day, it's different. During the day, when the sun comes and hits the earth and it's reflected away, the air above the earth is warmed up, it rises up, and it condenses on the upper part of the atmosphere. So this person producing sound, that sound is not going to be very easy transmitted to person C. It's going to be refracted towards the cooler part of the air, which is on the upper side. And that's why, like we said in our last lesson, this is the reason why maybe very early in the morning for Muslims, when there's a call for prayer, it can be heard over a long distance. But during the daytime, it may not be heard over a long distance because of the sunlight shining, and therefore the sound is refracted upwards, so it will not be heard by a person who is even this distance closer to the source. And the third quality or property of sound is what we call diffraction. Diffraction is the movement of waves through obstacle or around obstacles. Here we have a diagram of two people talking about some juicy gossip here. They are in this room, and there's a door at this point. There's someone else in the next room, and there's a door at that point. These people are talking very loudly. Could be about yesterday's football match, could be about what they saw on TV or a movie. Some juicy gossip here. Now, because the sound wave that is being produced will travel in all directions, it will go through this aperture, which is the door or window. It will be diffracted out, and it will go on and on and on. And then, because there's another aperture at this point, could be a window, could be a door, the sound wave will move in there, and the person who is in the next room can be able to easily hear what the people are talking about. Okay? So they can be able to easily hear what they're talking about. So, diffraction, the movement of waves through obstacles or around obstacles, can allow the person in the next room to perceive what these people are talking about. And that's why you can hear people talking from the next room or from somewhere else, because the sound will be diffracted through windows and through doors. Now, why is it not possible for light to be diffracted as much as sound? Now, this is simple. The wavelength of light is about 0.0005 millimeters. That is far much smaller than the gap on the door, because doors are normally about a meter wide or something, or actually it should be more than that. But light waves are much smaller than that, and therefore you cannot have a case of diffraction in that sense. So, because of what we know about sound being diffracted and sound being reflected, we can use those different methods to measure the speed of sound. Two methods. The first method is using what we call visible loud event. For example, a gun being fired or a cannon being fired, like in this case, there will be light that comes out. So if someone uses a stopwatch over some distance, of course, assuming that you know the distance between the source and the person on this other side, turn on the stopwatch when you see the lighting. Then pause it when you perceive the sound and see how long that has taken. Then, of course, knowing this distance here and knowing the time taken from the time the light was seen to the time the sound was perceived, you can be able to calculate the speed of sound. Distance divided by sound. Now, because of the fact that this is can be very fast, the distance has to be as long as can be, and it needs to be done several times. Then the average of this calculation will be taken to be the speed of sound in this place. Remember, speed of sound is affected by wind. So if wind is blowing in the opposite direction, or in this direction, it will affect the speed of sound in this case. So that can be used to calculate the speed of sound in this situation. Good example of that is this question here. A group of students measured the time taken between seeing and hearing another student 250 meters away, clashing two pieces of wood together. They obtained the following timing: 0.73 seconds, 0.78, 0.69, 0.81, and 0.77. So use their measurement to obtain the speed of sound estimate. What you do here is to add all the timings, then divide by 5. And that gives us the average. The average timing is 0.756 seconds. The distance we know was 250 meters. So use that distance divided by speed, divided by time, and gives you the approximate speed of sound to be 331 meters per second. The second way of determining the speed of sound is by using echo. Okay, so in this case, what will happen is someone with two boards keeps on clapping over time, and then trying to perceive when exactly on which beat that this person perceive or get the reflected sound, which is echo. So you can do that like 20 times, and you count 1, 2, 3, all the way to 20. Measure the distance between the clapping and the obstacle, and that will be the distance. So take 20 times 2d, that is the speed will be the same as the total distance divided by the total time taken for the 20 claps. Total distance between this person and the obstacle and the time for the 2 claps, and you can calculate your speed of sound. For example, an experiment to measure the speed of sound by the echo method. When a student stands 75 meters away from a wall, 20 claps are heard over a time period of 8.77 seconds. To calculate the speed of sound. Okay, we calculate the distance moved, it will be 20 times 2 times 75 because it goes and comes back. Goes and comes back. It was done 20 times. So calculate the distance traveled, 3,000 meters over that time of 8.77 seconds over the 20 claps, and get your speed to be 342 meters per second. Now it is different from the first one because, like we said, the speed of sound depends on other factors like temperature, wind, humidity, and all that. Okay, so sound is a longitudinal wave that in air consists of a series of compressions and rarefactions. It travels fastest through solids, but not at all through a vacuum. A reflected sound is called an echo, and this sound also undergoes refraction. And on average, humans can hear sound of frequencies from 20 Hz to 20,000 Hz. So in short, we have described what sound waves are, more of sound waves. We have looked more at the properties of sound waves, reflection, refraction, and diffraction. We have talked about the application of sound in what we call sonar, sounding, and ultrasound. And then we will look at a few mathematical examples on the same. So what you need to do here is to answer the questions on the topic of waves and sound in your textbooks. Answer these questions in your excess books. We have been talking about waves and then now sounds. At the end of these 2 chapters in your textbooks, there are questions. Answer these questions in your excess books. See you next time.